Hi, my name is Jakub, this is Krzysiek, and today we'll be talking about Rust, why we choose it to build our project, why we use it today, and why we didn't stick to C, which was the previous implementation of the Ariadna project. So, our presentation schedule looks like this. First is the introduction, as always. And then we go to the embassy, a little bit of introduction and how we used it in our project. Yeah, so let's begin. Yeah, so we are KoNaR, and student interest group active on Wrocław University of Science and Technology for about 20 years. 21 in October, I believe. And we are doing robots. That's the name. So recently we started using Rust in one of our flagship projects, Ariadna, which is this robot. The pic is slightly outdated. It looks way better now. You have to believe us. And yeah, we basically started using we programmed all embedded systems in Rust at this point. So, why did we choose Rust? The first thing, and the most major thing, was that code in C wasn't working properly when we came to the project. There were a little bit of trouble with RC pilot, and robots just randomly stopped working sometimes. We didn't know why. So that was the main reason. The other reasons are that the most, for me at least, the most logical thing to using Rust was that it's memory safe, which is really important in embedded systems, as you may part of hardware, which is also important in embedded programming. And register operations are inherently unsafe. So when you have to do this kind of memory manipulation, you put them in an unsafe block, and you know that, hey, you have to pay attention. This code may cause trouble. There is nothing like this in C. You can make a pointer to some random memory, location and pray that you did the right thing. Yeah. So that's about why we.
Okay, so this is an example code from Ariadna project. It was before the Rust revolution that came a year ago. The code should set different GPIOs depending on input information that was received via CAN frame. Yeah, it's look big. It's look like mess, and I don't have a good words about it. And in Rust, we can pretty much simplify all of that code to a few lines, and to be exact, it's one line. But only the formatter made it like separated the lines. So pretty much all of the project that was rewritten from C to Rust was made in purpose to be more clear, easy to use, and not faster to run, but faster to work with.
Yeah. Also, I would also like to talk a bit about popularity of embedded Rust, which is rising from year to year. On repo that's linked, you have an entire library of community-made drivers, hardware abstraction layers, and other stuff that's needed to properly develop embedded applications, such as frameworks and toolkits. And as a bit of fun fact, Rust also made its way to the Linux kernel. It's currently used as to develop toolchain, but I hope we'll get more of it there soon. Yeah, so now we will go to the embedded basics in Rust. How to set up an environment, how to do a little first program, how to set up a debugger, you know, the basics. So let's continue. Yeah, so first things first, you need to install Rust. You cannot program, I mean, you can program in Rust in browser, but it's not, you can't program embedded Rust without Rust. You need to obviously install correct target for your desired processor. This one is for the Nucleo 476 STM32 Nucleo. You can also install debuggers and an IDE of your choice. Most of you will probably install OpenOCD. There is also a Rust-made adapter called Probe-rs on top of the OpenOCD that you can use to debug your program. And it's really easy to set up. It even has its own Visual Studio Code extension, so if you program in VS Code, then I would recommend it. Then you can install cargo generate. It's not required, but with that tool you can essentially generate a template to make a simple embedded program, or not simple, just an embedded program, without manually having to make the files and such. Then you have to set up memory-x file, which is necessary for your programmer to link properly to the processor, and then you can start programming.
Okay, so a little more about setup of Rust. When I first came to the Ariadna project, to start programming in C, well, it took a lot of effort. There was a whole page of documentation about where to download your targets. You needed to download generated somehow CMake file, which where edits were pretty much impossible to make. So adding a new pins to adding new peripherals, adding new pins was pretty much impossible if you didn't knew how to do this before. In Rust, those 4 or even 3 lines of code can generate you a whole project. You don't need to download some shady targets from website and then link it in CMake file. You can just add it via command, and it's same, and the target is the same for everyone. So there's no need to worry that someone will download wrong target, link it with CMake, and the project won't start. And you spend hours and hours questioning yourself why it doesn't work, what I did wrong. In Rust, it's pretty simple. Everyone can run those 3 commands and start programming in Rust embedded.
Yeah, and a bit about Probe-rs. It's a Rust written linker that we use in our project to program the embedded systems in our robots, and not only in our robots. And to install it, you just put this in your terminal and then install some tools with cargo, which is another advantage of cargo. If you programmed in Rust before, you will know that you can make specific apps that use the cargo system. Yeah, and with Probe-rs you can program all of those listed processors here. There are hundreds of them. And you can also write your own flash algorithms if you desire to so.
So again, a fun story with the project. In C, there was a bash file which had commands to flash a program, and if you didn't know how to make one, you were pretty clueless. You have nowhere to go. You needed someone, some expert, the person that knew how to make those flash algorithms and make one for you, because you could nowhere go. Without the bash file that will flash the algorithm to your processor, you can write code and what? The program will do nothing because it will never be on a processor. And with Probe-rs, it's a lot easier. You can simply add target via Rastap. You can run Probe-rs, select chip, just write the name of the chip, and then the path to your program. It's one command line. It supports hundreds, if not dozens, of targets, and nowadays I think it's the easiest way of flashing programs in any language. With Probe-rs you can flash programs written in Rust, C, or even MicroPython. So if you don't want program in Rust, or you have to stick with C because it's older project and you can't rewrite it in Rust, starting using Probe-rs could be a really meaningful change.
Yeah, and since most of the embedded Rust is in open source, there are hundreds, if not thousands, of hardware abstraction layers available. But the one I found most complete is the STM32 HAL2, and it supports those processors that you can, the abstraction layer for STM, of course, not for every processor. And there is more and more coming in the future. And there is an example program built with this whole. Yeah. Yeah. All right. So we're there. First thing you'll notice, there is no std library in embedded Rust. Because some of the built-in methods of std library are using global allocators, which are kind of problematic. You would have to write your own one to use them in embedded programming. Then we have our usual use crates that are included. Then we include the STM HAL. And after that, there is a declaration of a mutex, which will change a flag in our program that allows us to change the state of our LED through a button press. Yes?
So the first thing that I was missing from the std libraries was most of the math functions. You can't use those fancy cosinus, arcus tangens, sinus. The most of the math functions are written in std library. So to use them in embedded, you need pretty much write them on your own or find some external library in GitHub that will support those math operations in embedded. The std library implementation uses dynamic allocation for most of the functions, and that's illegal in embedded programming, at least from a Rust point of view. So to calculate those functions, you need a new library that use heapless functions, that use heapless structures, and is safe for memory. Yes, there's core, but core is a really simplified version of std library, and the core is missing a lot of functions. Like I said before, Arcus tangens, that I will show later in example, is available on std library, but is missing from core. I don't know why it's not implemented in core. I haven't looked that far, but to have those functions, you need to reach the for externals libraries.
As far as I'm aware, no. You can call iterators in embedded programs. At least it was. Yeah. It would. Yeah. Couldn't be me. Yeah. So continuing with our program, we basically have a whole setup in main. It returns the exclamation mark because it needs to be. It's an infinite function, and you can see there is one unsafe block that unmasks interrupts. In Embassy, that we'll show later, you don't need to do this. It's already abstracted for you, so you don't have to see those menacing unsafe blocks. Yeah, and after that there is an interrupt that gets a flag from your interrupt, and with that it sets a let high or low. As I said, a basic program. What's interesting here are the pin setups, or should I say LED setups that creates objects, pin objects, constructors that really simplify the whole setup process for embedded programs, as you will see later. Yeah. So now we will come to the clue of the presentation, the Embassy. Embassy is an embedded asynchronic framework. That's pretty much, I love it. It allows for easy programming, async functions in embedded, which is real. I didn't. Never mind. And it's about just as fast as any C RTOS, but Embassy itself is not an RTOS, it's a framework. Yeah, basically.
Okay. Now let's move to a little explanation on how does Embassy work. So I think some of you know how does FreeRTOS works, the interrupt-driven concurrency, but in Embassy it's a little simpler. We don't need interrupts to decide which function needs to start when. Embassy uses async trait from Rust, and by this it decides when function needs to be completed, or the part of the function needs to be completed. So each task is separated to fragments divided by the async trait. When we write .async in code, that means we will wait for the completion of the part, and then we can move to the next part of the code. If there are multiple tasks, that's where the embassy starts to work really well. If one of the tasks reach the async function, async trait, it's stopped. The task is stopped. It goes to the executor pool and waits for its turn. Then the second task can finally run and reach the next async keyword, and then return to the pool again. So when we have a lot of tasks, there's a little queue created in executor that decides which part of code runs, and each task needs to wait for its turn. So there's no race for completion of the tasks that occurs in interrupt-driven concurrency.
I would like to mention that it's all done at compilation time, so it comes with no runtime cost. Yeah, for more reading about Embassy, there's a whole book that you can use. It's really well written. It essentially contains everything that you need to know to properly start developing in this framework. Yeah, and there are many examples for many kinds of processors. And for those processors, there are a lot of, basic stuff such as I2C, CAN, PWM.
This is official Embassy repository on GitHub. For me, it's a relief that something like that exists. You don't have to remember how to communicate via I2C or how to communicate via UART. Those parts are already written in those examples. You can just go to the GitHub, grab some functions, and paste it to your code, and then configure those functions to your needs. So you don't have to really remember how to use I2C in that exact framework, because you can work with RTOS, you can work with RTIC, you can work with barebone programming, and there's a lot of hardware abstraction layers, a lot of code that you need to remember, and Embassy simplifies that. If you don't remember how to do such a thing, one thing in Embassy, you can just look it up in the repository.
Yeah, and there will be the Embassy example of a hardest program I ever written, probably. The Blink. Yeah, as you can see, it's a little bit shorter than the button toggled one, but it works. Well, it's not button toggled, it's a timer-based application. But as you can see, there is a main executor that spawns your asynchronous tasks that make stuff for you.
Okay, so our Embassy code can be a little bit scary. Because that pre-code that you need, Embassy has a lot of includes, a lot of use cases, and it's really ugly for me. But if you leave those uses in some main file and write your code in separate files, it's become all clean and beautiful. So as I said later, not later, before, there's that async keyword and await keyword. And what does it do? When this task reach the async await keyword, it returns to the executor and waits for its turn. Because in this example there's only one task, there's only one task in queue. So it runs like there was all written in main.
Yeah, and then we have another example with a few more tasks, I believe, that shows how the whole framework works, essentially. And there we use defmt, which is a logging framework that's really convenient to use. It allows you to format your terminal outputs in many different ways. It's amazing.
So we talked about defmt, and now I will show you how does this defmt really simplifies all of the work. Because how to really read a variable in asynchronous program when when the register can take a lot of different values when another tasks are called. And here we'll just flash it. It's the beautiful example of the magnetometer in that L4 Nucleo board. As we can see, it's all printed via I/O input from a programmer, and we can have a lot of that prints. It doesn't slow program much, but it takes a lot of place in Flash, a lot of memory in Flash. Okay.
Yeah, essentially it's really convenient for debugging. You can use different levels of information, I would say. You can have the info macro, you can have the standard print line macro, and you can have also the warning macro. That also works. Yeah. Ooh. Okay.
So, where's my mouse? Oh. As you can see in the code, we have two macros to print out something. Because it's really bothersome to constantly comment and uncomment some lines of code with example prints. So defmt have a different level of printing strings, and we can choose while compiling via terminal variable we can choose which level of the print info we choose. In this example, we only want warn info to be displayed, and it shows the heading of the compass based on magnetometer. And if we delete that restriction to only show warn, it will display all of possible prints that are written in program. We can also, well, it's an ugly mess in that example. The beautiful part of Rust programming is object-oriented programming. Because the compass that I showed you earlier is just a struct. It has its own methods. You don't need to pass some structures like in C. It's all clear and friendly to the end user and programmer. The struct in embedded can take interfaces like I2C, UART, or PWM. So there's no need to remember which peripheral you need to use in what fragment of code. You just assign that peripheral to the struct of an object, then write some read functions for that struct, and you can really simply use that later in code. That was all examples in STM32 processor. Embassy also supports a lot of different processors. Like, for example, RP2030. It's a Raspberry Pi Pico board. Embassy also supports ESP32 processors and some of AVR at Megas. Some of Nucleo Arduino board isn't supported by Embassy. That's a shame.
Yeah.
What's on the horizon? 82. I'm not sure if it's on the horizon or if it's already in Embassy. I will check. Because processor Embassy has a lot of targets that it supports. It's really hard to remember which processors you can use on it when you don't work with it. But if you go to the previous slide about Embassy examples that they are maintaining, there's a list of all processors that Embassy supports and examples for them. So if you will find that one in that example, that means it's supported. For future plans, I don't know, really.
I tried to check, but I couldn't find it that fast, and we are reaching our time limit, so we will continue the presentation. The next thing on our schedule is how we use Embassy in Ariadna, our flagship robot. So yeah, the structure looks like this. It's basically, everything is basically controlled by CAN frames, not controlled, but communicated by CAN frames. And right now we have two main boards and more on the way. And essentially the EMU RC receiver actuators and GPS are contained on one board, and power board monitors the battery level and temperature of the whole robot. And it uses the CAN magistral to communicate with Jetson and O-Drive, which is our DC motor driver. And in a while, we will see the implementation, I believe. Yeah, that's our main function in Ariadna.
So the main functions in Embassy are really simple. all of you do in the main function, you just spawn the tasks that you want to run in the processor. For if you decide to don't use GPS, it's simple as just uncommenting the line, and now GPS will not be read. Nothing will be done with GPS.
I would like to also mention that we make all of our initializations here in that let R equals make static, which is a certain library in Rust that you can use. And we basically took an inspiration from RTIC. If some of you used it, then you will know. We basically make a big struct with all of our resources, and with that we pass them to the functions that need them, essentially. Yeah, and as you can see, we even have some cargo docs here.
Yeah, if you want to ask why everything is as shared, so that means everything is in mutex. That's because sometimes different tasks need to use same peripheral. The best example is KAN. Every task that handles IMU or that handles GPS need to use that KAN peripheral. So to make sure it is safe for processor to use that peripheral, we stick everything in mutex, and if tasks needs to send something via KAN, it just logs that mutex, send data through it, and then release it. I will later show how it works exactly.
Yeah.
So if we want to send linear acceleration from IMU, we just get that data from the IMU struct, because the data is stored in the struct. We encode it to KAN frame and then transmit it via KAN. KAN is made to have abstraction, the transmit function. So the ugly part of unwrapping, awaiting, and the debug code is hidden under abstraction. Also, when you are using diffmt, it's a different level of logging. It allows you to write external program that analyzes those messages sent by processor, and then you can calculate time differences in those messages, so you know how fast the function was completed, how much time it took to send the frame, or in what intervals are some frames sent. Like in IMU board, it was crucial to send frames in 20 hertz rate. So to analyze if everything is working correctly, the external program was used that collected those outputs from processor and then printed the result of the sending frame analysis.
Yeah, I would like to mention that you can also make a different implementation of KAN, for example, using channels or channels that just allow you to pass data through task asynchronously. It's used in the power board, it's not used in the RC board, and it allows you to not make KAN a shared resource, for example. It allows for a little bit of different approach to this problem.
When we said earlier about separating the code from a hardware code from software code, in the RC function and methods, we use a separate library to decode data received from RC to actual data that can be sent further to the O-drive system that controls our engines. Like, for example, actions is defined in external library, also written by us. The code don't use embassy, so it can be written in separate module and can have a test written for it.
Yeah, for example, you can you will just make a separate crate that can compile on any target, for example, x86 for your Linux system, and then you can write unit tests and properly check this without the need of physical boards near you. That simplifies the whole debugging process and streamlines the development. You can also integrate those tests in GitLab pipelines if you desire to.